Welcome Tashians, to Sleep By, the place where cosmic mysteries drift gently into your imagination like soft waves rolling across a quiet shore. Tonight, we explore a strange visitor from deep interstellar space. 3I Atlas, the third known interstellar object to pass through our solar system, and the surprising possibility that it may have released mini-objects, fragments, or smaller bodies that drifted with it. Harvard astrophysicist Avi Loeb, known for his work on interstellar anomalies, has suggested evidence that these fragments may reveal clues about the nature, origin, and history of this mysterious traveler. So settle in, relax your breathing, and let your thoughts drift outward into the calm, starlit ocean of the universe, as we explore one of the quietest but most fascinating cosmic stories unfolding above us. To understand 3I Atlas, you first need to imagine the quiet, endless calm of interstellar space, a place so vast and so empty that even light seems to wander through it like a traveler with no particular destination. This darkness between the stars is not completely void, but it is gentle, sparse, and silent in a way that nothing on Earth can truly replicate. Against that backdrop, imagine a lone object drifting for millions, perhaps billions, of years, shaped only by the soft pull of passing stars and the delicate pressure of distant starlight. This object, small and unassuming, carries with it a history written in the language of cosmic time. When it finally crosses paths with our solar system, we give it a name that reflects its status as a visitor from the great beyond. And that name is 3I Atlas. It is the third known interstellar object ever detected, following 1I Oumuamua and 2I Borisov. And its arrival provides yet another rare chance to study something born in another star system entirely. It entered the outer edges of our solar system. 3I Atlas did not announce itself with dramatic motion or bright activity. Instead, it moved with the patient grace typical of objects untethered to the gravitational rhythms of the sun. Astronomers describe its trajectory as hyperbolic, meaning that it is not bound to the sun's orbit and will eventually drift back out into interstellar space. Its path is a gentle arc carved through the darkness, revealing that it came from far beyond the Oort cloud, from a region of space unimaginably distant. The discovery was made by the Atlas Survey, a system designed to spot hazardous asteroids. But occasionally it finds something far more intriguing, something that whispers of worlds beyond. Our own science community approached 3I Atlas with the same careful curiosity that accompanied the study of the two interstellar objects before it. However, 3I Atlas stands apart because it exhibits qualities that are subtle, delicate, and puzzling in their own way. Observations revealed a faint tail-like structure, suggesting that the object might be losing material or interacting with solar radiation. Unlike Borisov, which behaved very much like a typical comet, 3I Atlas displays an unusual fragility, almost as if it is made of loosely held pieces that carry memories of earlier collisions or forces unknown. This fragility adds to the calm mystery of the object, because each piece is a clue to how such bodies form in faraway systems. To fully appreciate what makes 3I Atlas special, it helps to understand why interstellar objects are so rare. The space between stars is incredibly vast, and even though many such objects probably wander through the galaxy, the chance that one passes through our solar system and is detected during that window is extraordinarily small. For most of human history, these cosmic travelers came and went unnoticed, slipping quietly through the planetary orbits without so much as a whisper. It was only in the past decade that technology advanced enough to spot such faint, fast-moving anomalies. Because of this, every interstellar object is treated like a message delivered across time, written in the strange and ancient material it carries. The material itself is one of the great mysteries. Where did 3I Atlas form? Was it born in a young, chaotic planetary system, flung away during the violent early years when stars are surrounded by disks of dust and rocks? Or was it expelled from a mature system after a gravitational dance with a gas giant or binary star? These questions linger in the background as scientists study the object's brightness, color, and behavior. Each of these details acts like a clue, helping astronomers reconstruct its long, silent journey. The object's surface may contain compounds unfamiliar to our solar system, shaped by radiation that Earth-based materials never encounter. Its interior may hold voids or fissures created over unimaginable spans of time, making it fragile and prone to shedding tiny fragments as it warms in the sun's light. Another important aspect of 3I Atlas is its speed. Interstellar objects travel faster than typical asteroids because they are not bound by the sun till they cross into its sphere of influence. When 3I Atlas was discovered, its velocity confirmed that it did not originate from any known solar orbit. This high speed also makes such objects transient and difficult to study, because they pass through the inner solar system relatively quickly, lingering only briefly before they are gone again. This fleeting nature adds to the quiet wonder surrounding these visitors, because scientists must work quickly and carefully to gather as much information as possible without disturbing the soft, fading trail the object leaves behind. For us audience accustomed to the idea of space exploration as something bold, high-tech, and full of motion, 3I Atlas offers a different kind of cosmic experience. It is not an object of spectacle, but one of reflection, a reminder that the universe contains mysteries that reveal themselves gently, patiently, and without urgency. It invites a calmer perspective, one that aligns with the spirit of science, to sleep by, encouraging listeners to slow their thoughts and imagine the serene drift of an ancient object passing quietly through the sun's domain. Instead of loud engines or bright explosions, we have a faint, distant traveler, shaped by forces older than human civilization. As we continue to study 3I Atlas, it becomes clear that even though its appearance is subtle, its scientific value is profound. It reminds us that the cosmos is full of objects that carry information from distant pasts and unknown places. It is a gentle messenger from another star, gliding through our solar system for a brief moment before returning to the deep quiet of interstellar space, leaving behind questions that inspire reflection, curiosity, and a sense of peaceful wonder. When astronomers first began studying 3I Atlas, they expected it to behave like the other interstellar objects previously observed. They thought it would pass through the solar system with a predictable brightness curve, a steady motion, and perhaps a faint tail caused by gentle warming as it approached the sun. But as telescopes continued to track it, something subtle and unexpected emerged. The light coming from 3I Atlas did not behave as a single, solid body should. Instead, the brightness fluctuated in a way that suggested complexity, almost as though the object was not just one traveler, but possibly several, moving closely together, like a small family of fragments drifting side by side through the solar wind. This delicate variation sparked curiosity, because it hinted that 3I Atlas might have released mini-objects, tiny fragments quietly separating from the main body during its journey. The idea of a silent breakup carries a kind of soft imagery that aligns with the calm nature of interstellar space. Space does not tear things apart with noise or violence the way earthly events do. Instead, processes unfold slowly, gradually, sometimes over thousands of years. If fragments did separate from 3I Atlas, they did so in a way that mirrors the gentle erosion of an ancient stone carried by a river, each small piece drifting away without hurry. As 3I Atlas entered the warmth of the inner solar system, small stresses may have built within it, awakening fractures that had been quietly waiting inside its cold structure. When those fractures reached a tipping point, they would have released tiny shards that drifted off, following slightly different paths. To astronomers observing from Earth, those subtle separations show up not as dramatic visuals, but as small changes in brightness and motion. The evidence for these mini-objects comes from careful analysis of how 3I Atlas reflects sunlight. In the vacuum of space, even the slightest difference in the size or number of reflecting surfaces can alter the measured light curve. Instead of showing a steady pattern, the object's brightness showed hints of irregularity, like overlapping signatures coming from more than one piece. Observers began to notice what looked like small trailing components, faint and difficult to distinguish, but consistent enough to suggest the presence of miniature companions. These tiny bodies would be extremely faint, perhaps only meters across or even smaller, making them nearly impossible to see directly. Yet their presence subtly shapes the data, like small ripples spreading across the surface of a still lake long after a pebble has been dropped in. Avi Loeb and other researchers took a particular interest in this behavior because the release of mini-objects is not something observed often in interstellar bodies. Although comets in our solar system frequently shed material, an interstellar visitor does so under different conditions. Its composition is unknown, its internal strength uncertain, and its exposure to our sun's heat is likely very different from anything it encountered before. This makes the breakup process both scientifically valuable and deeply intriguing. If 3I Atlas released fragments, those fragments may reveal clues about what interstellar material is like, how it behaves, and what kind of environment shaped it in its home system. The smooth, almost meditative drifting of these fragments speaks to the quiet physics of deep space, where forces work slowly but persistently over unimaginable timescales. The motion of these mini-objects also offers insight into the past of 3I Atlas. Each tiny fragment carries information about the mechanical structure of the parent body. If the fragments formed through natural splitting, their distribution tells scientists how cohesive the original object was. If they were ejected more energetically, they might reveal pressure buildup within the object's core. The gentle separation of these pieces can even help reconstruct how long the object had been fragmented before it was discovered, because the spacing between fragments increases subtly with time. To astronomers, these drifting pieces are like soft fingerprints left behind by a traveler whose true nature remains mostly hidden. The reason the potential mini-objects matter is that they make the whole system more dynamic. Instead of studying a single point of light, scientists now have to consider how multiple bodies interact with sunlight, solar radiation pressure, and the gravitational landscape of the inner solar system. Solar radiation pressure, for example, affects small fragments more strongly than larger ones. If 3I Atlas released pieces only a few meters across, those pieces would be pushed gently by sunlight in a way that causes them to drift at slightly different speeds. This can produce observable differences in their paths, making the system appear more spread out. To the Earth-based observer, watching these motions through carefully collected data is like watching dust motes floating softly in a sunbeam, each one moving in its own peaceful rhythms. Scientists observe these clues. They also consider the possibility of past events that may have weakened the structure of 3I Atlas long before it entered our solar neighborhood. Many interstellar objects are believed to have experienced close encounters with stars, supernova shockwaves, or dense molecular clouds during their long travels. Each encounter could have chipped away at their surfaces or opened tiny cracks within them. When these ancient stresses combine with the warmth of the sun, even a small increase in temperature can cause ice or volatile materials to expand, gently pushing fragments outward. Over time, this leads to a soft, quiet breakup, rather than a sudden shattering. This image of slow, drifting release fits perfectly with the calm, meditative tone of the Science to Sleep by approach for us audience listening in a restful setting. The idea of these fragments drifting away can be imagined almost like autumn leaves falling from a tree, each one letting go at its own pace and floating downward without rush. Except here, the falling motion is not downward, but outward, away from the parent body, carried by the subtle push of sunlight and the faint gravitational contours of the solar system. It turns a complex astrophysical process into a gentle, visual experience, something easy to picture as you relax into the exploration of the cosmos. Ultimately, the evidence for released mini-objects from 3I Atlas contributes to a deeper understanding of how interstellar bodies behave when they encounter new environments. It reveals that even something as small and faint as a drifting fragment can hold enormous scientific value, and it transforms the object from a solitary traveler into a small, fragile cluster of companions moving together through the quiet sea of space. Studying these fragments allows scientists to glimpse the hidden history of an object that has traveled further than any spacecraft humanity has ever launched, making each tiny piece a messenger from another world. softly whispering its story as it passes through the sunlight of our star. When 3 Atlas entered the attention of astronomers, it did so quietly, without spectacle, as if it were another faint comet drifting along the deep corridors of space. But for Avi Loeb, the Harvard astrophysicist known for his willingness to question assumptions and entertain unconventional possibilities within scientific boundaries, the arrival of this interstellar object represented more than just another data point. It represented an opportunity to deepen our understanding of the universe by looking closely at the anomalies, the small deviations, the subtle clues that others might overlook. Loeb approaches objects like 3I Atlas with a blend of curiosity, skepticism, and a desire to think beyond the familiar boundaries of planetary science. His interpretations invite us to pay attention to the tiny shifts in light, the faint irregularities, the quiet signals embedded within seemingly ordinary observations. Loeb's interest in interstellar objects began long before 3 Atlas appeared. When Oumuamua, the first known interstellar object, passed through the solar system in 2017, it arrived with an unusual shape, an unexpected acceleration, and no detectable gas emissions, even though it behaved in ways similar to a comet. This intrigued him, not because he jumped immediately to extraordinary conclusions, but because he noticed that the object did not fit comfortably inside any of the known categories astronomers typically use. When the second interstellar visitor, Borisov, showed up behaving very much like a normal comet, Loeb saw that as important too, demonstrated that not all interstellar objects would behave in strange or unexpected ways. But it also reinforced the idea that anomalies should not be dismissed simply because they are rare. When 3I Atlas was discovered, it became a third opportunity to compare, contrast, and refine our understanding of these mysterious wanderers from beyond the solar system. In studying 3I Atlas, Loeb focused on the subtle evidence suggesting that it may have released mini-objects or fragments. To him, these clues were not just signs of a natural breakup. They were part of a broader pattern worth examining. Patterns, especially those that emerge from multiple unrelated observations, often carry deeper meaning in science. Loeb's interpretation encourages scientists to consider whether interstellar objects may come in a wider variety of forms and behaviors than previously thought. Instead of assuming that all interstellar bodies are simply comets or asteroids from distant systems, he suggests that some may reflect processes we are not familiar with, formed under conditions that exist far beyond our astronomical neighborhood. His perspective is not that these objects are artificial, but that we should not treat that possibility as off-limits in scientific inquiry. His focus remains on gathering data, interpreting the anomalies, and allowing the evidence to guide the questions rather than limiting questions to match existing expectations. One of the reasons Loeb's involvement is so significant is that he emphasizes the importance of approaching cosmic phenomena with an open but disciplined mind. He often describes science as a process that must allow for the unfamiliar. When faced with an object like 3I Atlas, whose faint fragmentation hints at unusual structural weaknesses or unknown internal composition, his interpretation helps highlight the value of humility in astronomy. The universe is far older, larger, and more diverse than anything humans have fully explored. And objects like 3I Atlas may represent materials or histories that have no direct counterpart in our solar system. For Loeb, this makes them especially valuable not because they fit existing theories, but because they challenge them gently. Inviting a deeper look, Loeb's analysis of the mini-object evidence begins with the brightness pattern of 3I Atlas. The fluctuations in brightness could be signs of fragmentation, but they also raise questions about the material properties of the object. Interstellar objects endure erosion from cosmic rays, exposure to high-energy radiation, and collisions with dust grains over millions of years. These processes can hollow out their interiors, weaken their surfaces, or create layers that separate easily once warm. Loeb suggests that the gentle shedding of fragments might provide insight into what kinds of materials survive long interstellar journeys and how they age in environments we cannot reproduce on Earth. These Ideas align with his broader view that interstellar objects are messengers carrying ancient information, a type of natural archive drifting through the galaxy. Another aspect of Loeb's interpretation involves the trajectory and motion of the fragments. He studies how solar radiation pressure interacts differently with small objects compared to larger ones. If the mini objects around 3I Atlas drifted in ways that did not match conventional models, this could reveal unique material properties or unusual surface characteristics. Loeb encourages researchers to analyze how the fragments respond to sunlight, how they scatter their reflected light, and how they spread out over time. Even though these motions appear delicate and quiet from our distant perspective, they contain valuable information encoded in their paths. The fragments become like soft traces of a story written in the language of orbital mechanics. A story that Loeb believes should be read carefully. One of the more intriguing areas of Loeb's work is his willingness to explore whether some interstellar objects might very rarely have artificial origins. He does not claim that 3I Atlas is one of them, nor does he present speculation without grounding it in measurable data. Instead, his approach is philosophical as much as scientific. He argues that dismissing such possibilities outright would limit the scientific method. If humanity is truly searching for signs of life or intelligence beyond Earth, then unusual objects passing near our planet deserve careful attention. This does not mean leaping to conclusions, but rather being willing to let the data speak, even when the data points towards something surprising. With 3I Atlas, the evidence for mini-fragments becomes an opportunity to ask whether such fragmentation has a natural cause, or whether it might represent a form of structure that is uncommon in our solar system. Loeb carefully reminds other scientists that nature itself produces extraordinary structures, and the universe may hold surprises we have not yet imagined. For us audience listening in the soft, relaxed state that science to sleep by is designed for, Loeb's interpretations provide a soothing form of intellectual openness. His voice in this conversation offers both reassurance and curiosity. It reassures because it remains rooted in scientific reasoning, using evidence as the guide. It stirs curiosity because it invites listeners to imagine a universe filled with diversity, subtlety, and quiet mysteries waiting to be uncovered. The idea that 3I Atlas may have carried mini objects drifting slowly through space becomes an invitation to reflect on how much remains unknown, how much there is still to explore, and how peaceful scientific discovery can feel when approached without haste or fear of the unfamiliar. To explore the mini objects potentially released by 3I Atlas is to enter a realm of quiet cosmic subtlety, where the smallest fragments carry immense scientific meaning and unfold their mysteries not through spectacle, but through gentle, almost whispered clues. These fragments, if they indeed separated from the main interstellar visitor, represent some of the oldest and most untouched materials we have ever had the chance to study. Their existence invites us to imagine a journey across the galaxy that began long before Earth formed, a journey shaped by the slow processes of cosmic erosion, distant starlight, and the delicate gravitational tides between stars. Understanding these mini objects means appreciating not just their presence, but the story of their formation, elution, and release into the solar system, all of which unfold in ways that encourage a soft, reflective exploration. Aligned perfectly with the calming tone of science to sleep by, the first question scientists consider is the composition of these fragments. What are they made of? Interstellar objects like 3I Atlas originate in planetary systems far beyond our own, so their material may include compounds and structures that do not commonly appear in our solar system. The fragments might contain exotic ices formed at temperatures far colder than any environment near Earth. They could also include grains shaped by cosmic rays, dust compacted by the pressure of radiation fields, or layers built up through the slow accumulation of atoms drifting through interstellar clouds. This type of material has been exposed to the deep, low-density environment of interstellar space for millions or billions of years. Over that vast span of time, radiation penetrates the surface layers of the object, altering molecular bonds in ways that scientists on Earth rarely encounter. If the fragments from 3I Atlas carry even a tiny portion of this altered material, They become like pages torn from a book that has been aging in silence. In the universe's most ancient library, behavior of these fragments also offers important clues. The way they moved, drifted, and interacted with sunlight reveals their structure and density. Smaller objects, especially those only a few meters or less in size, respond much more dramatically to radiation pressure from the sun. When light strikes a tiny fragment in space, the momentum of that light can gently nudge the object, pushing it off course over long periods of time. If the mini-objects released by 3I Atlas were lightweight, porous, or filled with voids created by cosmic wear, they would drift more easily than denser, rock-like fragments. This would create a soft spreading pattern, where each fragment slowly separates from the others the way fireflies drift apart in a dark field. Their paths guided by quiet influences that operate beyond the threshold of human senses. Scientists, studying these trails of drifting fragments, interpret them like ancient scribes reading the faint strokes of a faded manuscript. Each subtle deviation in motion tells a story about internal structure. A fragment that accelerates more than expected under solar radiation might have a lower density. One that rotates irregularly might have an uneven surface, shaped by countless microscopic impacts from interstellar dust. Another might tumble in a slow, unsteady rhythm, suggesting that it is shaped more like a chipped shard than a smooth pebble. These motions contain no sound, no vibration, no dramatic turbulence, only the tranquil mechanics of space quietly revealing the inner complexity of an object older than human civilization. A third important aspect of the mini-objects involves their thermal behavior. When interstellar fragments enter the inner solar system, they experience a warm environment compared to the deep cold of interstellar space. This warming can cause gases trapped inside them to expand gently and escape. In a comet from our own solar system, this process often leads to bright jets or obvious comas. But in an interstellar fragment, the effect might be much softer, producing slight outgassing that subtly alters the fragment's trajectory. The behavior would be so gentle that it might go unnoticed without precise measurements, but its presence would suggest a composition that includes volatile compounds preserved across eons. The release of these compounds could also be responsible for some of the separation events that caused the mini-objects to drift away from 3I Atlas in the first place. As scientists deepen their investigation, they also consider how these fragments might have formed long before 3I Atlas entered our detection range. Interstellar objects often endure intense conditions. They may be heated by passing close to a star, cooled for millions of years in absolute darkness, or struck by high-energy particles that shatter microscopic parts of their structure. These experiences build internal stresses, invisible but persistent, waiting for the right moment to release. When 3I Atlas approached our Sun, the increase in temperature may have triggered the expansion of trapped ices or awakened tiny fractures that had been dormant for ages. These fractures could have led to slow, quiet separations of small pieces, nothing explosive or sudden, just the gentle loosening of fragments that had long been held together by fragile bonds weakened over time. Understanding these fragments also means acknowledging the vastness of their history. Each piece may have begun as part of a much larger body formed near a distant star. That body might have been shaped by processes similar to those in our early solar system, collisions between planetesimals, gravitational sculpting by young planets, or heating from a newly ignited sun. At some point, perhaps during a chaotic gravitational encounter, the original object was launched out of its home system, becoming a wanderer in the galaxy. Over time, cosmic erosion shaved away portions of it, and internal stresses introduced fractures that eventually produced the fragments observed today. In this sense, each mini-object is like a memory shard, holding information about a place humanity has never seen and conditions that no spacecraft has yet visited. For us audience listening late in the evening, imagining the fragments drifting alongside 3I Atlas can feel like a gentle meditation on time and motion. These are objects that have traveled farther than any human probe, carrying with them the quiet signature of ancient cosmic environments. Their paths are shaped not by engines or thrust, but by the soft, persistent forces of nature, sunlight, gravity, and the cumulative effects of a long, silent journey between the stars. To imagine these fragments is to picture something delicate and serene, moving in unison with the slow rhythms of the universe. Studying these mini-objects expands our understanding of what interstellar debris looks like, how it behaves, and what it can tell us about the galaxy beyond our solar system. Their presence around 3I Atlas reminds us that even the smallest objects drifting through space can hold deep significance. They are tiny, quiet messengers from distant origins, offering us an opportunity to learn more about the diversity of materials that form in other star systems and the processes that shape them. Over cosmic time escalesis, 3I Atlas entered our solar system and began its quiet passage toward the Sun. It carried with it a story written in motion and unfolding narrative, expressed through subtle shifts in speed, direction, and illumination. To understand this journey is to appreciate how interstellar objects behave when exposed to forces very different from those they experienced in the environments where they originated. The path of 3I Atlas, and the possible motion of its mini-objects, reveals not only the mechanics of celestial travel, but also the gentle interplay of sunlight, gravity, and ancient structure acting on material that has been wandering the galaxy for longer than Earth has existed. The calm rhythm of this movement aligns beautifully with the science to sleep by atmosphere, allowing listeners to visualize the slow drift of matter through space as something soothing and meditative, a cosmic dance performed in silence. When 3I Atlas first crossed the boundary into our solar system, it encountered the gravitational influence of the Sun, which began to shape its trajectory into a long, sweeping arc. Interstellar objects travel at high velocities, but even at these speeds, their paths bend gently under the pull of our star. This bending motion is predictable and can be modeled with great precision, yet, for an object like 3I Atlas, its interaction with solar gravity also helps scientists detect subtle deviations that may indicate fragmentation. If mini-objects separated from the primary body, they would diverge slightly from the main trajectory, each following its own graceful curve, determined by its size, mass, and orientation. To astronomers, these tiny divergences are like soft brushstrokes on the canvas of space, revealing details about the object's integrity and internal structure without producing any noise or visible disruption. As 3I Atlas continued inward, sunlight played a larger role in shaping its behavior. Sunlight exerts pressure not forceful or violent, but gentle, persistent, like a slow breeze pushing on a thin sail. This radiation pressure affects smaller fragments more easily than the main body, meaning the mini-objects would begin drifting in ways subtly different from the parent object. Over time, these differences widen the distance between them. A small fragment only a few meters wide might be nudged noticeably by the momentum of sunlight, altering its path as it glides closer to the Sun. These slow divergences occur far too gradually for the eye to catch, but instruments tracking 3I Atlas can detect their presence through faint changes in brightness and position. This drifting is so calm and soft that it becomes almost hypnotic to imagine tiny particles, each millions of miles from Earth, moving like dust floating in a sunbeam, guided only by the quiet push of light. One of the most intriguing aspects of the journey involves the thermal energy the object receives. In the deep cold of interstellar space, the surface and interior of such an object remain frozen solid, locked in temperatures near absolute zero. When 3I Atlas approached the Sun, its surface warmed gradually, causing internal ices to expand and release trapped gases. This outgassing, though incredibly faint, can act like a series of almost imperceptible jets, gently altering the object's rotation or nudging fragments outward. If the mini-objects separated during this warming phase, they might have done so quietly, carried away by the most delicate release of energy. Unlike a typical comet from within our solar system, which may erupt with visible jets, an interstellar object like 3I Atlas produces such modest activity that it appears nearly still. This subdued behavior contributes to the mystery surrounding its mini-fragments, suggesting that their release was not dramatic, but soft and gradual, unfolding over days or weeks as the warmth slowly penetrated the body. the motion of the mini-objects also reveals information about their structure. Small fragments tumbling through space can rotate in complex ways. Some might spin with slow consistency, like a leaf turning gently in a breeze, while others might wobble irregularly, shaped by uneven surfaces or internal voids. The rotation of these fragments affects how they reflect sunlight, creating flickers in brightness that astronomers record as light curves. These light curves, though consisting of simple changes in brightness, provide deep insight into the fragments' shapes, orientations, and even their histories. Scientists can analyze these flickers the way one might listen to soft whispers, extracting meaning from the faintest variations. For a listener imagining this in a relaxed state, it becomes easy to picture these fragments drifting silently, each carrying a rhythm of rotation that began long before humanity existed as the object approached the inner solar system. Gravitational interactions with planets also played a subtle but measurable role. Though 3I Atlas never passed extremely close to any major planet, even distant gravitational pulls can create tiny shifts in trajectory. These small influences can separate fragments further from the main body, amplifying the drift already caused by sunlight and thermal outgassing. Over long distances, such tiny forces accumulate, shaping the pattern of motion that astronomers later reconstruct. This is not a chaotic or explosive process, but a slow choreography guided by the invisible lines of gravitational fields that connect the solar system like a vast, silent web. Each mini-object follows its own thread along this web, creating a soft, expanding formation as they continue their journey. The passage of 3I Atlas also offers a glimpse into how interstellar material behaves in an environment rich with solar activity. Solar wind, a stream of charged particles flowing outward from the sun, creates a gentle pressure on small fragments, especially those with charged surfaces. This interaction can cause the fragments to drift in directions that differ slightly from the main object, adding another layer of complexity to the pattern of motion. Even though these effects are subtle, they are measurable with sensitive instruments. For a calm listening experience, the idea of solar wind softly brushing against these fragments can feel like an extension of nature's quiet touch, shaping their journey without sound or disturbance. When 3I Atlas began its exit from the inner solar system, moving once again toward the outer regions, where sunlight weakens and temperatures fall, the dynamics shifted again. The radiation pressure decreased, the thermal expansion slowed, and the motion of the fragments became more uniform. They continued drifting, but now in a more steady and unchanging pattern, like small boats carried by a long, gentle current. Their paths, now set, would lead them away from the sun and eventually back into interstellar space, continuing the ancient journey they had been on long before being seen by people on Earth. To reflect on this journey is to recognize the serenity of cosmic motion. The behavior of 3I Atlas and its mini-objects is not chaotic or explosive, but soft and measured, shaped by forces that act slowly and steadily across unthinkable distances. This understanding transforms the object from an astronomical curiosity into a quiet traveler moving through the solar system in harmony with the universe's natural rhythms. For us audience listening to this narrative at the end of a long day, the drifting of these fragments becomes an image of peaceful motion, matter from distant stars gliding past our own, touching nothing, disturbing nothing, simply continuing its long voyage through the calm and infinite dark of space. A quiet disintegration of an interstellar object is unlike anything we typically witness within our own solar system, because these bodies carry with them an ancient fragility that has been sculpted not by one star, but by the long, lonely wandering between many. When scientists explore the possibility that 3I Atlas released small fragments in a natural process, they imagine an object shaped by extremes of heat and cold, by cosmic radiation, and by the slow, relentless pressure of time. A natural breakup does not happen all at once, and it rarely looks dramatic. Instead, it appears as a gradual softening, a weakening beneath the surface, a subtle separation of old layers that have held together for perhaps millions of years. When astronomers look back at the faint light from 3I Atlas and consider that its mini-objects may have drifted away gently, They visualize something closer to ice flaking from a frozen cliff, or small pebbles loosening from a rock face as the seasons shift. These are quiet events, unhurried and almost meditative. Speaking of slow cosmic processes rather than violent ones. In interstellar space, an object like 3I Atlas lives in a constant cycle of thermal stress. During its journey between stars, the temperature surrounding it plunges toward absolute zero, but as it enters the inner solar system, sunlight begins to fall on its surface, warming the outer layers. This warming is incredibly gentle compared to heating near a star, yet even mild light can trigger expansion in the upper crust of an object that has been dormant in deep freeze for an unimaginable length of time. Expansion at the surface meets resistance from colder, deeper layers, which still cling to their original shape. Over time, this tug-of-war creates cracks that slowly spread downward like thin silver threads. These cracks do not roar open or shatter the object. Instead, they whisper, forming pathways where grains, dust, or small fragments may eventually separate from the main body. Even cosmic radiation plays a role in this delicate process. During its long passage through the galaxy, 3I Atlas would have been exposed to a steady rain of high-energy particles that strike its surface and burrow shallowly inward. Over millions of years, these particles can weaken chemical bonds or cause molecular-level rearrangements within the material. The results take ages to accumulate, but eventually the outer layers become brittle. When the object makes its approach into the solar system and begins to warm, these brittle zones can flake and lift away with minimal provocation. Some of the fragments that astronomers detect may come from nothing more dramatic than pieces gently shedding, following their own tiny trajectories as they drift apart in the sunlight. Another natural mechanism that scientists consider is rotational stress. Interstellar objects often spin, and although many spin slowly, some rotate quickly enough to create centrifugal forces that work against the integrity of their structure. If 3I Atlas had an uneven shape or internal density variations, its rotation could gently pull at weaker regions, encouraging small elements to drift free. These fragments would not shoot off suddenly. They would simply ease away from the main body, following curves determined by the object's rotation and the faint gravitational interactions between them. Over weeks or months, this kind of separation could produce a small cluster of companion particles moving along with the object, each one reflecting a tiny bit of sunlight and leaving a faint trail behind it. Outgassing is another phenomenon that scientists watch closely when studying objects like comets or icy interstellar bodies. If 3I Atlas contained frozen volatile materials, such as carbon dioxide or methane, even mild warming from sunlight could cause these substances to sublimate. As the gas escapes, it can push gently against the surrounding material. These soft jets can lift dust or pebbles from the surface and suspend them in the faint envelope surrounding the object. From a distance, this appears as a diffuse cloud, but within that cloud may be discrete fragments that eventually settle into their own paths. The process resembles the way frost melts off a window as the morning sun rises. Small crystals sliding away before dissolving into mist. As 3I Atlas moved through the solar system, the interplay between sunlight, internal structure, and the quiet physics of fragment separation created conditions where many objects could form naturally. Each fragment becomes a small world of its own, carrying the same ancient signature as the parent body. These fragments provide clues to the internal composition and mechanical history of the object. By studying how they move, how they scatter light, and how they drift relative to the main body, scientists can reverse engineer the breakup process. They gain insights into how interstellar materials age, how they respond to environmental changes, and how long-term cosmic weathering shapes their strength. When astronomers model the natural breakup of objects like 3I Atlas, they imagine countless interactions happening beneath the surface over millions of years. Tiny grains rearranging, pores expanding as microscopic ice melts and refreezes, internal fractures slowing creeping outward. The interstellar medium is not entirely empty. It contains dust and particles that collide with traveling objects at high speeds, each impact leaving behind small damage that accumulates over unimaginable distances. When the object finally reaches the warm light of a star, these accumulated weaknesses reveal themselves. Some areas soften, others crumble, and the many objects that observers detect become testaments to the long journey behind them. Fragments, released in a natural breakup, also follow predictable physics once they begin to drift. Solar radiation pressure pushes them gently like wind moving fallen leaves. Gravity from nearby planets pulls them slightly off their original course. Even magnetic fields can influence some of the dust-sized pieces. All of these forces work together in a slow ballet that leaves a pattern in the sky, a faint memory of the moment when the object shared parts of itself with the space around it. The release of small fragments from an interstellar traveler embodies the calm, patient nature of cosmic evolution. It is not a violent process, but a gradual loosening shaped by time, temperature, and the quiet pressures of existence far from any star. Each mini-object becomes a drifting reminder of the ancient past of Three-Eye Atlas, offering a glimpse into the subtle mechanisms that gently reshape the oldest wanderers in the galaxy. When we look at an interstellar object like Three-Eye Atlas and consider the possibility that it released small fragments along its path, we begin to realize how deeply such events can inform our understanding of the space between stars. The interstellar medium is often imagined as a silent void, a near-perfect emptiness stretching endlessly in all directions, but in reality holds a delicate and complex mixture of dust, ions, gases, radiation fields, and drifting particles. The mini-objects that accompany an interstellar traveler carry the signatures of this medium imprinted on their surfaces and within their structures, giving scientists rare opportunities to examine how ancient matter evolves while journeying through regions that no human spacecraft has ever reached. The quiet fragments of Three-Eye Atlas can serve as tiny messengers from environments so distant and extreme that they can only be studied indirectly, helping researchers understand how matter behaves and transforms across cosmic distances. To appreciate what these small pieces might reveal, it helps to imagine the journey that Three-Eye Atlas undertook long before it entered our solar system. It may have formed near a distant star, in a region filled with icy grains and dense molecular clouds. Over the course of millions of years, gravitational encounters or stellar winds could have knocked it out of its birthplace, pushing it into the open sea of the galaxy, where the interstellar medium becomes thinner, colder, and more serene. As it drifted through this vast expanse, its surface was shaped by accumulating dust grains that struck it at high velocities, each impact leaving a microscopic scar. Cosmic rays bombarded its exterior, triggering chemical changes that transformed its surface into a darkened, weathered skin. If the object carried internal ice or volatiles, these elements would have slowly migrated and ray-frozen depending on minute temperature fluctuations that occurred over unfathomable spans of time. Every tiny variation leaves subtle marks, and those marks accumulate in ways that tell a story of the places it has traveled. Many objects released from the parent body would carry these same markings. If they separated long before the object arrived in our solar system, they might show evidence of harsh cosmic processing. Surface chemistry could indicate exposure to ultraviolet radiation unfiltered by any nearby star. The texture of their outer layers might reveal whether they spent eons drifting freely or if they stayed shielded within Three-Eye Atlas until only recently emerging. Scientists analyzing such fragments through telescopic observations often look for how they scatter light, since these scattering patterns can indicate whether the grains are smooth or porous, icy or mineral-based, compact or loosely aggregated. Even though these fragments may be too distant or small for direct sampling, the way they reflect sunlight becomes a kind of whisper from faraway environments. Understanding the interstellar medium through fragments like these also involves studying how they move. The trajectory of a small object is influenced not only by gravity, but also by pressure from starlight, magnetic interactions, and collisions with unseen particles. When scientists track the paths of mini-objects released from Three-Eye Atlas, they can observe subtle deviations from purely gravitational motion. These deviations offer clues about the environment through which the fragments have been traveling. For instance, if a fragment moves slightly differently than expected, it could indicate that it is being pushed more strongly by solar radiation than larger pieces. This helps researchers infer its size, shape, density, and reflectivity, all of which relate back to the composition and texture it developed in interstellar space. Such data also allow scientists to refine models of the interstellar medium, adjusting estimates of its density, particle distribution, and the influence of large-scale magnetic fields. The fragments can additionally offer insights into variations within the interstellar medium itself. The galaxy is not uniform. It contains pockets of dense gas, regions of ionized material, and empty stretches where dust is sparse. As an object travels through these different zones, the interactions it experiences leave behind chemical signatures. At times, molecular clouds may deposit certain compounds onto an object's surface. At other times, intense radiation fields may strip away lighter elements. The presence or absence of certain materials on a fragment can therefore act like a record of the environments it has passed through. In some cases, scientists may identify molecular residue or mineral coatings that point to specific types of regions, such as areas rich in carbon-based compounds or zones influenced by supernova events. Each fragment becomes a piece of a cosmic puzzle, helping researchers reconstruct the object's path across the galaxy. Studying these tiny bodies also enriches our understanding of the early formation of planetary systems beyond our own. If 3I Atlas originated from the outskirts of another star's protoplanetary disk, then the materials within its fragments may mirror the building blocks from which planets, moons, and asteroids formed elsewhere. Differences in composition may indicate whether the fragment came from a system with a hotter central star, a denser disk of gas, or a region where volatile ices were more abundant. This can help astronomers compare the conditions under which different planetary systems evolve. It may even offer subtle insights into what kinds of worlds could form under varying chemical and environmental circumstances across the galaxy. Fragment behavior can also teach scientists about the longevity and durability of materials in interstellar space. Over long timescales, cosmic rays cause erosion at the molecular level, gradually altering the structure of ice, rock, and dust. By estimating how long certain features on a fragment's surface have been exposed, researchers can infer how long that piece has been traveling independently of its parent body. This helps refine models of how long interstellar objects remain intact before gradually breaking down. If 3I Atlas released multiple fragments at different times during its journey, the condition of each fragment could reflect a different stage of its evolution, offering a layered history of exposure to the interstellar environment. The wider scientific value of such fragments becomes even more profound when considered alongside other interstellar objects that have visited our solar system. With each new object observed, astronomers expand their understanding of what typical interstellar travelers look like and how they behave. Some, like Oumuamua, exhibited unusual acceleration possibly linked to solar radiation pressure or volatile release. Others, like 2I Borisov, behaved more like familiar comets. If 3I Atlas released mini-objects, the patterns, timing, and distribution of those fragments could help determine whether fragmentation is common among interstellar visitors or if it is more likely to happen only under specific circumstances. By comparing these behaviors, scientists can begin to classify interstellar objects more effectively, grouping them based on their origins, compositions, or structural histories. Ultimately, the study of mini-objects around interstellar travelers is not just a matter of mapping debris. It is a way of listening to the quiet messages carried by matter that has spent ages in the galaxy's most remote regions. Each tiny fragment offers a faint but meaningful echo of the conditions that shaped it, the environments it endured, and the forces that gently altered its form. By observing and interpreting these clues, researchers deepen their understanding of the interstellar medium and the broader galactic ecosystem through which stars, planets, and cosmic bodies continually move, interact, and evolve. As we look ahead to the future of studying interstellar objects like 3I Atlas and the quiet fragments that may accompany them, we begin to imagine a new era in which humanity's understanding of the galaxy deepens in ways that once felt unreachable. The discovery of interstellar visitors has already transformed the way scientists think about the space beyond our solar system, shifting the focus from distant starlight and faint radio signals to actual physical objects that drift close enough for us to observe directly. These objects bring with them stories written in their surfaces, their shapes, their compositions, and even the behavior of the small fragments that trail behind them. With every new observation, the boundary between the known and the unknown softens, opening pathways toward discoveries we are only beginning to anticipate. The future of interstellar object research is not defined by dramatic breakthroughs, but by steady, patient accumulation of insight. Much like the gentle layering of sediment on the floor of a quiet ocean, the most transformative step in this field will come from powerful telescopes designed to scan the sky continuously. The Vera C. Rubin Observatory, with its legacy survey of space and time, will soon begin capturing the night sky in unprecedented detail, revisiting the same regions every few nights. This steady rhythm of observation will allow astronomers to detect faint, fast-moving visitors that might otherwise slip through unnoticed. Interstellar objects travel quickly, often on trajectories that differ subtly from those of comets and asteroids that orbit the Sun. These differences become easier to catch when the sky is monitored systematically and frequently. The new observatory will act like a gentle heartbeat of discovery, pulsing through the night, revealing objects that have wandered across the galaxy for millions of years before drifting into our field of view. In addition to discovering more interstellar visitors, future instruments will be able to track them with increasing precision. Tiny fragments that break off from objects like 3 Atlas may have been too faint or small to detect with earlier telescopes, but advances in image resolution and sensitivity will allow scientists to follow these quiet companions as they glide along their paths. Observing their motion more clearly will help researchers understand how fragmentation occurs, how fast the pieces drift apart. In time, its light diminished until only the most sensitive instruments could find it, and then eventually even those signals began to blur into the background noise of the universe. Yet even as it disappeared from view, its presence persisted in the data, in the charts and models that continued to evolve in labs and observatories. That persistence, the quiet endurance of its record, mirrors the object's own journey, a continuity that refuses to fade entirely. For astronomers, this endurance is both scientific and emotional. Every recorded path, every plotted point, feels like a thread connecting humanity to the larger movement of the cosmos. As the journey of 3 Atlas fades beyond the range of our telescopes, what remains is not the object itself, but the quiet understanding it leaves behind. It came from a place we cannot name, traveled through a darkness we cannot measure, and offered us a fleeting moment of connection across the endless expanse of space. For scientists, it was a discovery that expanded the boundaries of what we know. For dreamers and listeners, it became a story, a reminder that the universe is not still, that it is always in motion, always speaking in the language of light and distance. 3i Atlas is a reflection of how exploration has always shaped the human spirit. Each time we look up, we search not only for the unknown, but for the reassurance that we are part of something larger. Its silent trajectory mirrors our own. We too are travelers moving through time, leaving traces of our passage in the data we record, in the art we create, in the memories we share. The cosmos has no urgency, yet it holds infinite stories. And each discovery, like Atlas, is an invitation to pause, breathe, and remember that we belong to this unfolding story. It is humbling to realize that while we watch 3i Atlas for only a moment, it has existed for millions of years, and will continue to exist long after we are gone. That awareness brings both smallness and serenity. In its infinite drift, it teaches us that even the briefest encounter between worlds can create meaning, that silence can hold entire symphonies, and that the act of observation itself is a form of connection. As 3i Atlas disappears into the black horizon of the interstellar sea, we are left not with absence, but with wonder. The data will fade, the brightness will diminish, But the story, this shared moment between the known and the infinite, will remain. Somewhere out there, beyond the reach of sunlight, it continues to move, carrying with it the echo of our curiosity, the trace of our attention, and the quiet acknowledgement that even in the deepest silence of space, something extraordinary is always happening. Good night.